All right, let's take a look at example 2. We have an f function and a g function. I went ahead and graphed them. The f function is cube, so if we looked in over here at that particular graph, we would see that this is our f function. Our g function is quadratic. It is a downward opening parabola, and so it actually is this graph right here. And what's interesting about these two equations is that they intersect multiple times, so they create two bounded regions. So we're going to find the area in this region and the area in this region, but it's important to take note that in this region right here, the f graph is on top of the g graph, but yet on this region, the g graph, the quadratic, is on top of the cube. So this is going to require us to set up two integrals, one each representing these regions here. It's also important for our integrals that we find the x coordinates of these points of intersection, because those are going to be our limits. So you could type this into y1, y2, graphically find all the x coordinates of these intersection points. Algebraically, you could set these two equations equal to each other. And as you can imagine, just by looking at them, setting these two equations equal to each other and then solving for 0 and trying to factor would be quite challenging. All right, so as we go through the setup of these integrals, I'll just give you the x coordinates of these intersections. And of course, you can verify with me by actually finding the intersections on your calculator. All right, so let's take care of finding the area in this region first. And go ahead and on all your graphs, what you need to do is produce a graph if one's not given, and then in every bounded region, just draw in your representative rectangle. So we know it's going to be a vertical rectangle. This is integration with respect to x. The thickness of each and every one of these rectangles is dx, a change in x. Okay, so that helps keep us on track as far as how to set this up. Notice that no matter what rectangle you choose in this region, that the top of every rectangle will always touch f of x, and the bottom of that rectangle will always touch the other curve g of x. Important to know. All right, so let's look at the integral that represents the area in the first region. The x coordinate of this point of intersection is -2. It's our lower limit. The x coordinate at which we're going to stop accumulating these rectangles, the x coordinate here is 0. Okay, and so the top function is our cube and the bottom function is our quadratic. So it's f minus g for this bounded region. And it would be okay to do f of x minus g of x dx. You get full credit, but I wanted to show you something, so I want to go ahead and use the actual equation. So f minus g. Okay, let me point out a mistake that's often made, and I want to kind of head you off on that. It's f, this is all f minus g. Oftentimes I'll see minus, and then students will just put down g, but you need to be aware that you're subtracting the entire g function. And because I have multiple terms, I have more than one term, unlike the last example, it's important to put this in parentheses, because when you subtract, you need to distribute and change the signs of all the terms that make up your bottom function. And don't forget your dx. Let's move on to the second region, new limits. All right, put in your representative rectangle. It could be anywhere in there. Okay, the top always touches the g function. The bottom of that rectangle, no matter what rectangle you put in here, will touch the other function, the f function. So this would look like g of x minus f of x dx. But I'm going to go ahead and put in the specific equations. We do need limits. So the left limit is 0, and this point of intersection, that was 2. All right, so top curve is g. Minus, and go ahead and put in parentheses, the f function. Because if you're subtracting f and it has multiple terms, again, you're going to have to distribute that negative, which would change the signs of every one of these terms. Okay, at this point you guys can see that, wow, this would be a lot of calculations as far as algebra, distributing, reverse power rule, calculations. You can go to the calculator, type this in as y1, go to the home screen, necessary keystrokes, find the values of each of these and add them together. Okay, and just to give you the answer so that we can move on and look at other examples, is the total area for this problem was 24. Okay, so at minimum, we're going to have to set up the integrals that represent the area and the regions, and then we can go to the calculator and get the value. Again, 24 is positive, that's good. If it wasn't, two things to look for. Maybe in the calculator you switch the limits, so be aware of that. That would cause you to have a negative answer. Or perhaps you have the wrong function on top and bottom. All right, so for example 3, the equations are here. Let's take a look at what this graph looks like. If they don't provide you a graph with a shaded region, it's up to us to produce the graph. So y equals square root of x. Y equals x minus 2. Okay, and this is important too. They tell us first quadrant, and that's because we want to ignore this space right here. We only want to look at the region in quadrant 1, which means without them saying so, we now want to consider y equals 0 to be a boundary line too. So we're looking at this region right here. Okay, so we want to find the area in that region. Well, we know the equations are solved for x, so it's integration with respect to x. Okay, studying this integral or this region for just a minute, draw in a representative rectangle. So maybe if I drew one in over here, it's important to note that the top of this rectangle touches the square root graph, but the bottom touches y equals 0. But the further you move to the right, and especially right here at this x-intercept of 2, 0, which we can find, it's the 0 of this linear function, right here something interesting happens. Okay. Okay, right after this x-intercept, if you draw in a representative rectangle right here, if that's where you chose to put it, the top still touches the square root graph, but the bottom now touches not y equals 0, but the linear function. So what this is telling us is that we really need to find the area in two different regions and add them together. So we need two integrals to represent this area. All right, so finding the limits that'll help us in setting up the integral, we can clearly see that this value right here is 0. This x-intercept is 2. The only other x value we need is the point of intersection that occurs right here, and that would be 4. And we can get that by setting these two equations equal to each other, or on the calculator, finding the intersection. So we've got the limits. We know what's on top and what's on bottom. It's time just to set up the integral. So for the first region right here, this region right here, okay, we're going to collect areas and rectangles from 0 to 2. The top function is the square root of x, and the bottom is 0. Do you have to show that? No. Easy enough to calculate without a calculator. Plus, okay, now the area in this region right here, okay, we're going to collect the area in rectangles from 2 to 4. Okay, the rectangles will always touch the square root graph, and the bottom on that region from x equals 2 to 4, the bottom of the rectangles will meet the x minus 2 equation. Okay, important to keep it in parentheses so we know to distribute and change all the signs. Okay, both of these would be easy to calculate by hand, but for the sake of time, let me just share the answer with you, and that's 10/3. Okay, I want to take the same example 3, and I want to look at integration with respect to y as another option if you would want to. So I'm going to draw another picture of this same region here because I'm going to put in some different rectangles. Square root and x minus 2. Okay, intersection point here, etc. Okay, this was integration with respect to x, previous. Okay, what if we want to integrate with respect to y? And if we think about that for just a minute, okay, if you were to put in not vertical but horizontal rectangles from the lowest y value to the highest y value up here, lay some in. Okay? No matter where you place these horizontal rectangles, you can see that the right side will always touch the linear function, and the left side of that same rectangle will touch the other curve, the square root graph. So if you were to integrate with respect to y, you wouldn't need two integrals, you would only need one. So that's definitely a benefit, that's a plus. The downside to this is that because these equations are already solved for y, I'm going to have to solve each of them for x to get a right minus left situation. So that's the disadvantage of integration with respect to y, is if the equations are not x equals, okay, we need to algebraically solve them to be in x equals if I'm going to do this integration. So I think I'll do that right here. So let me take y equals square root of x, square both sides, easy enough. So x equals y squared. So this right here, okay, can be considered x equals y, x equals y squared. Okay, let's take the other equation and solve it for x. Add the two on the trade side. So x is equal to y plus 2. So this equation is x equals y plus 2. All right, continuing with integration with respect to y, the thickness of each of these horizontal rectangles is a change in y, this little thickness here. So we need to get an expression that represents how long it is. So that's going to be your right x minus your left x. Okay, something else to consider too is our limits. Remember, our limits in integration with respect to y wouldn't be x limits, they're y limits. So if we want to stay in the first quadrant, our smallest y is 0, and then we need to know, well, what is this y coordinate of this point of intersection? Not the x, but the y. And I believe this point of intersection is 4, 2. So 4, 2. So that means that this y is 2. So the advantage again is that it only requires one integral, but we have to solve the equations for x equal, and we have to pay attention to the fact that we now need y limits. So y is 0, y goes to 2. The right curve is y plus 2, and the left curve is y squared. Integration with respect to y, the thickness of each of those rectangles. Okay, so now that we have this set up, that's the only integral that's required. Just think of y as a dummy variable. I could change it to any letter of the alphabet or any whatever I wanted to, and integrate using the reverse power rule. It doesn't have to be y. It can go in the calculator, but it doesn't have to be y. It could be all x's, and it's just the setup that we got over here, and the y limits that doesn't make it, doesn't make it, what am I trying to say, strange that we're using an x. Okay, so it just is the variable we use to set it up. So everything's good to go. If you were to do this in your calculator, I encourage you to pause and check, put it into y1 with x's, go to the home screen, use these as your limits. You should get the same value, 10/3. And it only took one integral. So for our next example, real quickly, if you're asked to find the area between these two curves and I identify that they have two equations solved for x equals, I know this is a right minus left situation. Okay, so I'm looking at the picture that likely will be provided. It'd be too difficult for you to sketch this graph in the time that we have. So there's background about having to sketch that. So they're likely going to provide the region. This is going to be a sideways opening parabola. I have it graphed here. Okay, and then if I draw on the vertical line x equals 2, I'm talking about this region in here. Because the equations are solved for x, that pretty much gives it away that you're integrating with respect to y, okay, because you have y's in your equations. So draw in your representative rectangle, and notice that no matter where you put a rectangle, the right side will always touch 2, and the left side will touch the smaller x value given by this equation right here. So one integral is necessary. Okay. The only thing left for us to find would be these y values right here. Okay. And likely they would be given. Okay. And if not, set these two equations equal to each other. Put 2 in for x here. So 2 equals, you have this equation. I would go to my calculator. I'd let y1 be 2, y2 be this equation with x's. I'd find the intersections. Okay, and then I would look at the x-coordinates, which would be the y-coordinates of this graph right here. But let me go ahead and give you these limits. All right, so this ordered pair right here is 2, comma, and the y-coordinate is 3.44949. 3.44949. And a word of caution, If there are more than 5 decimals, write them all down, because we're going to be using this as a limit to calculate a final answer. And if you round this too soon, your final answer isn't going to be accurate enough. So at least 5 decimals. This point of intersection is 2 comma, and this y-coordinate is negative 1.44949. Likely you'll be given these right here, the points of intersection, so you can take note of what you're using as far as your limits are concerned. Better yet, it'd probably be good to store each of these limits into maybe some variable. If you're comfortable with your calculator and the store feature, you might want to store each of these in, and then you can use those letters in the keystrokes that you use to find the answer to an integral. And if you're not familiar with that, then we will be practicing that. All right, so let's do the setup that represents the area in this region. Okay, to keep myself on track, I always like to do this first because I know I'm differentiating with respect to y, so that just reminds me that everything in my integrand needs to have a y in it if there is a variable. So lower y value, negative 1.44949, and up here. If I did assign a value to each of these limits, if I called this a equals a and equals b, and somewhere on my paper I showed that this was equal to a and this was equal to b, then in my setup I could put a and b here. So it just saves me some writing. All right, the right x, so the bigger x, which is 2, minus the smaller x, so 2 minus, be sure and use parentheses, I get this right here. All right, as indicated by the decimal limits, this would likely be a calculator problem because I can't imagine doing the necessary algebra, finding an antiderivative, and plugging these in. So I would think that this would be strictly a calculator question. And if so, I might do a little work over here, distribute the negative, clean it up, put it into y1, go to the home screen, and then do the keystroke that would get you the answer. And again, remember, this is a dummy variable now. When you go to put this into y1 after you clean it up, you're not putting in the letter y, you're putting in the letter x. The final answer, 19.596. And this key was done quite some time ago, so I would like in the future to keep this answer out to at least 5 decimals. I didn't on this particular key. All right, so I know that's not a lot of examples, only 4, but I'm hopeful that through these 4 examples you have an understanding of how to set up integrals that represent area and regions, and what some of the limitations and challenges may be. It's all about paying attention to that representative rectangle. So it's required that you graph the functions given if they're not if the graph's not provided, and it's required that you draw in that representative rectangle. And at least draw in several of them so you can see that maybe there are multiple integrals that need to be used to find the total area. So just kind of be mindful of that and know that the graph is expected, and the setup of the integral, and then if you're using a calculator, that's it, the setup of the integral. All right, so hopefully this was helpful.